I was watching a video about the flat Earth and how you could not calculate the distance to the moon. And I decided I was going to do a little bit of research to see if it was even possible to measure the distance to the moon. And obviously we have. And what was interesting was some of the videos indicated that the ancient Greeks were able to calculate the distance to the moon. And also, because they were able to figure out the distance to the moon, they also calculated the distance to the sun. And anyways, I found this article. I'll leave in the description below how the Greeks went about calculating the distance to the moon. And so I've been running some experiments myself, and I will describe the first part of it, which was how can you go about calculating this number here? How can you figure out the length of the shadow? Now, in short, you've got any kind of object, whether it's a ball in your hand, whether it's a rock in your hand, whether it's a telephone pole, whatever, will cast a shadow from the sun. So the sun puts light rays out in all directions. It will strike an object, and the object will block the sun and will create a shadow. Now, the thing about that is that the sun is not a pinpoint of light. It's actually a ball, which means that this diagram doesn't really cover it, but the light that comes from this spot will shine in this direction and will also shine in this direction here. So this object would block this, would cast a shadow here if it was just this one pinpoint of light. But now we've got a pinpoint over here that radiates in all directions as well. So this one would cast light in this direction and in this direction. And basically the part that's shaded here is the part that is completely blocked by this object. So how did they go about calculating this 108 Earth diameters long? And I'll get to that in a minute. So if the moon was on this side of the Earth and the sun was over here, the moon would cast a cone like this that they've just turned around and flipped around this way, so it's pointing back towards the sun. But this is the orbit of the moon around the Earth. And because the moon is the same size in the sky as the sun, that it creates a taper right down to more or less the surface of the Earth, but this diagram has it shown towards the middle of the Earth. So the way they've done this, they were able to calculate the diameter of the Earth, and they were able to calculate the shadow cast by the Earth. So they had one shadow. So this here is the Earth's diameter. This is the moon's diameter. And by observing the moon transit the Earth's shadow, they were able to calculate how many moons could fit inside the Earth's shadow, which they figured was 2.5 moon diameters. And because each of these have the same angle, they were able to figure out the length of the moon. So the first thing that I really wanted to do was to figure out how did they get the 108. And it turns out that if we take 108 and we invert that and we do the arc tangent is 0.5305 degrees. And I don't have, I'll do that now. Okay, I tried to find it. I couldn't find the answer. Maybe I'll put a snapshot of where I found it in the video. The shadow cast is basically the arc that the sun occupies in the sky. That's a half a degree. And you take the tangent of that. So you can imagine that if the sun's over here and we are over here, then the distance here over the distance here is going to be half a degree. So if we take this divided by this, it's the tangent of this angle here. So that's how they got that number. So the first thing I wanted to do was to be able to take a measurement that the ancient Greeks could have done easily. And the first thing I thought of would be to use a pinhole camera to simulate what it would have been like in antiquity if they had a barn, for example, and there was a crack in the barn wall. First thing I did was I made myself a very crude pinhole camera. I took an old box of crackers, cut the ends off, and on this side I taped on a kind of like a tissue paper on this side, which was reasonably translucent. Then on the other side, I just put a regular sheet of paper and I made a hole that would simulate a hole on the side of the barn, for example. And this side, you could imagine would be the other side of the barn. And if they were inside, they'd be able to see the light that was projected on the inside of the wall. And this is an example of having it pointing towards the light, towards the sun. You can see how it created a spot here where the sun is. So that was the first thing that I did. I then took a video of that and kind of line it up into the camera without looking into the sun. And at some point, I locked the focus so that the camera wouldn't try to autofocus, and then I just kept moving the thing closer and further away from the camera until I could find a frame like this that was in focus. I exported that one frame. Actually, I exported 3 separate frames, which I'll get to in a minute. So the measuring tape is used to calibrate the number of pixels per millimeter. And I'm going to bring up this here. So the first frame is this one. And all I did was I just duplicated the thing in a separate layer and played around with the brightness levels. Tighten everything back down because I wanted to make sure that I would catch as much of the light as possible. And then I did the tape measure, so from here to here, so 10 millimeters, 160 to 170 happens to be 199.1 pixels. So 199.1 pixels per 10 millimeters, so it's 19.91 pixels per millimeter. Then in this one, I did something similar. The hole is not quite round. I used a pin to create a hole, and I guess it didn't create it quite round enough. You can kind of see it here. These edges are slightly in compared to the rest of it. And that kind of created something like this. So then I would just go in and kind of find where the light was still shining through, like right about there. And then I just took the measurements. So in this case here, it would be, for example, 48 pixels. So I've got a document that I have all of this information. The length of the camera is 230 millimeters. There we go. So this is the length, 230 millimeters. So the next thing that I did was I tried to calculate a reasonable accurate pixels per millimeter value. So I took 3 separate stills. 10 millimeters is 199.2 pixels. And the sun it's somewhere around 48.3 pixels. And if I take that and divide that by pixels per millimeter, I get 2.42 millimeters. So I did the same thing for the several other stills, and I get roughly the same value. The size of the pinhole I did something similar. So I figured that the size of the pinhole was about 0.489 millimeters. So now I needed to calculate the angle of the sun. So the sun was 2.4 millimeters on the view screen, and the hole was 0.48 millimeters in diameter. And if the pinhole was literally a point in space, then the entire light cast on the screen on the back would be the angle. But because we have a hole that has a certain length to it, I needed to calculate I needed to subtract this from the resulting output to be able to get the angle. So by subtracting 0.48 millimeters from 2.4, I got 1.93 millimeters spread out over 230 millimeters, which worked out to 0.482 degrees. And that's pretty close to the 0.5. Frame 2 was somewhat similar. I got 0.518. Frame 3 was again similar. I got 0.501 degrees. So I was able to replicate roughly 0.5 degrees. And then at that point, I needed to calculate the cone, what I call the cone ratio. It's the distance that it's the distance of the shadow cast for its diameter. And I ended up using each of the angles that were measured, and I also created an average angle, and so I've got 4 different ratios. So they said 108, and I had calculated 110 all the way up to 118, but the average was 114. That was the first solar angle measurement experiment that I conducted.